Reconstructing a crash or predicting a flight trajectory requires us to connect three specific data points: position, velocity, and acceleration. These stacked graphs represent an elevator's motion. Velocity is position slope. Every incline change on the top curve creates a flat plateau on the velocity graph below. This relationship repeats. Velocity slope dictates acceleration, translating angled lines into rectangular spikes. When that bottom graph is a straight horizontal line, acceleration is constant. In this specific state, the math of motion simplifies into the 5 kinematic equations. Every standard one-dimensional motion problem involves a set of 5 variables: displacement, initial velocity, final velocity, acceleration, and time. To solve for any of them, you only need to identify 3. From there, you solve for the 4th and treat the 5th variable as irrelevant to that specific calculation. These formulas represent the standard equations for constant acceleration. The missing quantity column on the right is your selection tool. By matching your irrelevant variable to this list, you isolate the exact equation required for the problem. Equation paralysis is solved by a process of elimination. Once you determine which variable isn't needed, the choice of formula is already made. Let's apply this to a free-fall scenario where a pitcher tosses a baseball straight up. At first glance, the problem seems to offer only one piece of data, an initial speed of 12 meters per second. But the physical conditions described provide the rest of the numbers we need. Take the description maximum height. At the very peak of its flight, the ball must momentarily stop before falling back down. In mathematical terms, its final velocity at that point is exactly 0. The prompt also specifies the ball is tossed into the air. Near Earth's surface, objects in free flight accelerate downward at 9.8 meters per second squared due to gravity. By translating these physical descriptions into numerical values, we secure the 3 variables necessary to solve any kinematics problem. Consistency with signs is critical. If we define the upward direction as positive, gravity is a downward force. Therefore, acceleration remains negative 9.8 throughout the entire flight, even while the ball is moving up. Let's test your understanding of these values. Pause the video and determine the ball's displacement if it is caught at the same height it was released. Take a moment to reach a conclusion. The displacement is 0. Because the starting and ending positions are identical, the net change in position is 0. Plugging that 0 displacement into the position equation creates a quadratic result. This math gives us 2 distinct times, t equals 0 at the moment of release, and a second time representing when the ball returns to the catcher. But what if the ball is not caught and instead falls past the pitcher to the ground? You don't need to restart the calculation for the downward leg. By setting the final position to a negative value representing the ground, the equation accounts for the entire trajectory in a single step. To solve these problems efficiently, maintain a clear workflow. List your 5 variables, use elimination to select your formula, and convert physical descriptions into numerical constants. Once you establish your known values and respect your sign conventions, the equations will do the work.